Welcome to Data Skeptic, a podcast exploring the methods, use cases, and consequences of recommender systems. Welcome to another installment of Data Skeptic Recommender Systems. It isn't a strict dichotomy, but oftentimes we think of features in machine learning as being handcrafted features or cases where we use representation learning to custom find those features. Handcrafted features are really where most things started in machine learning, and they still play a significant, and I'm sure will continue to play a significant role in many ML rollouts, but you can't deny how popular representation learning is getting. And for good reason. If the model can learn its own features, let it. But then you're left with this latent space that's quite hard to interpret. Handcrafted features let you give an insight to a user different from, well, the cosine similarity was very high between two vectors. So all is not lost. There's many interpretability techniques, and one idea in particular we're going to delve into today called disentanglement. This is the idea that different factors should really be independent of one another. In that regard, perhaps you could move along the axis of one in sort of a perturbation study. And the degree to which your model is disentangled gives you a lot of flexibility. It's really a great tool for interpretability, or at least it would seem so. Our guest today, Irvin, and his co-author surveyed the literature on disentanglement representation learning and recommender systems, and they noticed most prior work really looked at disentanglement qualitatively rather than in a rigorous way. So they set out to go from qualitative to quantitative and found some really interesting insights along the way.
I'm Ervin Dervishai. I'm a third-year PhD student at the University of Copenhagen. I'm studying mainly machine learning and specifically recommender systems, focusing on representation learning for recommender systems, and more recently, large language models and their applicability in the recommender system space.
What first got you interested in recommender systems?
It all sort of started during my master's. I had a course in recommender systems and I got hooked on the subject from that moment on. Then I participated with a group from the University Politecnico di Milano, where I was doing my master's, joined the university team that took part in the Rexis Challenge in 2018 in Vancouver. After that, I got interested even more in the subject and decided to do my master's thesis in recommender systems. From that moment on, I decided to pursue a PhD in the topic.
Very cool. For listeners who aren't familiar with the term, could you share your perspective? What is representation learning?
So representation learning is the way that computers take in huge amount of data and try to build their own understanding, their own representation of this data, and then they use it to build decision-making on top of that representation.
So I'm familiar with the idea of feature engineering. Let's say we're working on fraud. Maybe we'd ask, have you used this credit card from this IP address before and had a successful transaction? I can handcraft all these features. Is that the same idea, or are you talking about something different?
Yeah, it's somewhat different because before, as you mentioned, we had this whole field of feature engineering where you'd put a lot of effort in trying to build these features that would help model to model better the task at hand. Whereas with representation learning, what you are trying to do is you just input all of this data to the model and then hope that whilst training, the model is going to make sense of the data on its own as a way trying to do better predictions.
Is that through an unsupervised process, or is it a supervised learning technique?
There are two paradigms. Both are used today, both in machine learning and recommender systems. In the unsupervised paradigm, what happens is that you do not have specific labels for your task at hand. And basically, you just leave the model to learn different representations for the data. And usually that involves some sort of clustering where you look at the different features, the model looks at the different features and sort of clusters the data. Whereas in the supervised paradigm, what happens is that you also have labels associated with your data. So you build a model that, given a certain input, tries to learn to predict the correct label for that input. And while doing so, internally, it has to build a representation for that input.
So the unsupervised version is very appealing to me because number one, it's kind of like I have no work. The algorithm's going to do it for me once I set it up. And maybe the algorithm can perform as good or better than I would and also do it faster. So I'd like to go unsupervised. Do you think the field is mature enough that that can be a practical thing industry people and researchers use?
I think for certain problems and certain tasks, you have to reside on unsupervised learning. The main reason, as I touched a bit upon, is the fact that you need to have labels in order to do supervised learning. And there are a lot of cases when you do not have access to this label. You just have a huge amount of data, and then you try to understand what can you use that data for. And there are also other cases when you do not even know the task. You just have the data, and you want to understand what's happening with that data, even before you know what you are going to use it for. So you use unsupervised learning to sort of learn different representations of the data. And of course, that can help you later on once you have a downstream task.
The unsupervised technique then produces a representation, usually a vector of numbers, and those numbers don't necessarily have column labels like my handcrafted features. Can I interpret the data that's being presented to me?
Yeah, in the case when you try to learn these representations with your models, be that either with the unsupervised paradigm, but also there are cases also in supervised paradigm, it becomes quite difficult to understand what the representation mean. So you would have, as you mentioned, a sort of a vector that is your representation for a specific input. And of course, when you do unsupervised learning, you do not know what you are looking for when you are learning this representation. So that brings an aspect of interpretability into the mix. And of course, this is a topic very, very important nowadays in machine learning.
Could you give an example of one or two popular techniques for interpretability, and especially if you find them useful in your work, and maybe describe them a little bit?
There are a couple of interpretability metrics that are very common and are used both in industry but also academia. One of them is LIME and the other one is SHEP. Basically, what these two methods do is they try to build some models that can be used to explain later on what each individual component within your embedding means. They try to connect these with specific labels in the input space in your input data.
So I think we've got a lot of the key ideas on the table. There's representation learning to come up with the vector. There's interpretability tools to help me maybe get a sense of what they are. Perhaps the other keyword from your title that we should focus on is disentanglement. Are representation disentanglements and interpretability linked in recommender models is the paper we're going to discuss. What is the disentanglement part?
So when you use these machine learning models or recommended system models, what happens is that when you leave the model to learn whatever representation of the data that it needs in order to accomplish as better as it can the task at hand, in this case, recommending items to specific user, it learns a representation such that the different components within that representation are sort of entangled with one another. I usually like to give the example of trying to buy a t-shirt, right? And when you're trying to recommend a specific item within the t-shirt section, there are a couple of components that are usually attributes that every user would look at. For example, you'd have the size of the t-shirt, but the other one could be also price. And of course, when doing the recommendation, you want to learn a representation such that these two components are disentangled from one another in the learned representation. And by that, I mean those are kind of invariant. If you change the size of your t-shirt, it shouldn't affect also the price. Or if you want to recommend something that is cheap or expensive, that shouldn't affect the size of the t-shirt that the user should be interested in based on their previous purchase history.
So getting into your research that we're going to discuss from this paper, could you outline the goals you had?
So we scouted the literature for disentangled representation learning models being used in recommender systems. And what we wanted to do with this study was to try and replicate their results in the form of a reproducibility study, and also investigate whether there is a connection between disentanglement and interpretability, and between disentanglement and recommendation performance.
So let's maybe focus the first one on the connection between disentanglement and interpretability. They seem like closely linked ideas. Could you contrast them? How do they actually differ?
The entire premise of learning disentangled representation is that you can find in the representation space, you can sort of separate these different aspects of a given input. And the idea here is that if you are able to do this separation, then the representation are more interpretable. And you can use that later on in the recommendation phase as a way to show to the user why they received certain recommendation in the UI or system that they're using.
So I'm thinking of something like movie recommendations. And let's say I, as a user, have contributed a bunch of feedback in some form, and it's clear I like horror movies. But maybe we have a disentanglement representation which also identifies duration. And then I'm thinking if you perturb duration for a user like me, it should just recommend shorter or longer horror films. These two factors are independent. Is that kind of the idea?
Yeah. So as I said, you try to learn these attributes within the disentangled representation, such that, as you mentioned, if you change only the genre or only the duration of the specific movie that you are interested in, the genre shouldn't change, right? So those would be totally separate entities within the recommendation model.
This feels very intuitive, but also a little ad hoc or a just so story or something like that. How can we study it empirically?
Right. So what we did to study this disentangled representation recommended system was to find models that other papers that were using these models in recommended systems, and we tried to collect the data sets that they were using, the different underlying machine learning models to do the disentangled representation. Yeah, so we started by collecting these models and these data sets. And what we found is that they were just focusing on a qualitative evaluation of the disentanglement. So even though they were presenting work that was focused on learning disentangled representation, eventually the evaluation of the disentangled space was mainly done from a qualitative point of view. What we wanted to do was to try and provide a quantitative evaluation of disentanglement. And to do that, we focused on some existing disentanglement metrics like disentanglement and completeness. And we evaluated these models on these two metrics.
Could we jump into some of your findings? It seems natural that good representations would correlate highly with interpretability, at least intuitively. Is that what you found?
Yeah, so we ran a correlation analysis between the interpretability metrics that we were using based on top of LIME and SHEP, and the disentanglement and completeness metrics from the disentanglement literature. And the correlation analysis actually indeed did show that there was a positive correlation between disentanglement and interpretability. This sort of goes in line with what our expectation was, because as you mentioned, the entire premise for learning disentangled representation, or at least one of the benefits of it, is that you end up with more interpretable representation.
So your work in this paper covers a wide variety of models and data sets. Did you find that correlation everywhere?
Actually, no. We found that the correlation, when you account for the different models that we were using, for those, we could see that the correlation would hold. Whereas when we accounted for some of the data sets, we found that on the majority of them, indeed, this connection still holds.
Would you say it holds strongly, or is it a slight correlation?
The correlation between the disentanglement and interpretability was quite strong. whereas the connection between the disentanglement and the effectiveness, the performance of the recommendation models, there we did not find consistent correlation, even though some of these models that we were evaluating were showing that disentanglement was a key component in the performance of their model.
So if historically that's been a key indicator in the model, is that because the maybe prior work focused in on limited data sets and it was, we could say, maybe a little bit overfit? Or how do you interpret it?
Yeah, so what we saw is that for some of these models, just because of the way that they were introduced and presented in the respective papers, some of the details were not given. So we had some troubles trying to replicate their scores. Also because when you consider disentangled representation learning, you also need some ground truth, right? So you need to know whether once you learn these factors of variation within the representation, you need to know which specific component or specific attributes this factor of variation relates to. Usually in recommended systems, we do not have such ground truth, and that makes it more difficult to sort of replicate the results of existing work. We try to follow as much as we could from the paper the results, the experiments of the presented work and the models that we were considering, but eventually we weren't able to reach the same scores that they were showing.
In terms of performance or reproducibility, you weren't able to reproduce the exact results of prior studies. Is that because those studies need to be more clear about some initialization? Or maybe you just had a different seed than they did? What can account for the differences?
So we tried in our reproducibility study to have multiple runs for our experiments, all with different seeds, and we eventually just reported the average of our runs. Indeed, in some of the papers in some of the models that we considered, we did not have all the details. Yes, the authors usually provide a specific range for the hyperparameters that they use within the models, but they did not provide the exact hyperparameters that they used to get the scores that they got. So we tried to, in our study, try to cover all the different extremes of the hyperparameters that they used, but still we weren't able to get to their scores.
So in my survey and people I talked to and other research I've read, it seems to me there's a common sense. People believe that disentanglement representations are like a gateway to both better recommendations and better interpretability. Maybe you found some better interpretability, but it's sounding like better recommendations are not a guarantee. Do you think the community should be surprised by this result? Or do you expect them to be surprised by that?
Yeah, in some sense, the result was also surprising for us, because when we read this other work, we saw that they were pushing for disentanglement as one way to achieve better recommendation performance. We did not find that connection in our results. But I think we should still strive for learning disentangled representation, because, as we discussed, it also brings the aspect of interpretability, which is very important, especially in recommender systems. In a way, with more interpretable recommendation, you also help build a bit more trust between the system, the recommender system, and the user. So I think it's still important to focus on learning disentangled presentations.
Well, I'm curious if you have any thoughts on why it didn't impact accuracy or the performance of the recommendations. It seems like it should intuitively. Maybe it's the case that the model already has the accuracy that it needs from the existing features and there's no benefit, or maybe there's something else going on here. Do you have a sense of why efficiency wasn't improved in terms of performance?
Yeah, so when you try to make the model more interpretable, and in this specific case, when we push the model to learn disentangled representations, this sort of acts like regularization on the network. So instead of leaving the network or the recommendation model free to decide which kind of representation it needs in order to do better in terms of recommendation performance, with disentangled representation, you are sort of regularizing the network, the model, and forcing it to build this interpretable representation, and that sort of penalizes the performance of the model.
So should we expect an efficiency improvement in terms of performance, or was that an unfair goal to have?
Yeah, in some ways, I think if you consider learning of disentangled representation as a regularizer, yeah, in that case, usually what happens is that you sacrifice a bit of performance and gain a bit more in explainability, in interpretability. So in some sense, yes, I would consider it expected to not observe the same connection that we saw with interpretability.
Could we talk more about that trade-off? Imagine you're in a new role in some big industry position. They have a recommender system with a lot of revenue behind it, something like that. It seems like they would push for highest accuracy, highest performance because they want to make the most money as a company. What would be the good argument for exploring the trade-off?
I think it's a very important component because, I mean, the main objective of a recommender system is to show the most accurate recommendation to the user. But eventually, in the end, you need to have trust from the user into the system, and I think that is quite important. Even before they get to the recommendation stage, they need to know that the recommendation that they are getting have some sense, and they are not just some mathematical computation of an underlying model. But if you can show explanations why the user is getting that specific recommendation, then they sort of believe more in the system and sort of accept more also the recommendation that they are getting. So in some sense, it can also help a provider of recommendation increase their retention of the users. Because, of course, if you increase trust, that also helps.
So I've seen a lot of ideas in the recommendation system literature about including some metadata with your recommendation, like why was this suggested to me? How do you feel about those approaches?
I think they are one of the components within, or one of the paradigms within the recommender system space, actually. So in those cases, when we try to use also some metadata or content information, we call that a content recommender system. And what that does is look into the similarity of the metadata between the items that the behavior of the user and a list of items that are potentially recommendable to the user. And that also helps making the recommendation more interpretable, because if you have in your behavior, you have watched movies with, I don't know, with a specific genre, then it's quite easy to show to the user a specific item, recommend it again from the same genre. We also see this in many different platforms where it says, because you liked this in the past. And that makes it much more easy for the user to understand why they got the specific recommendation.
Along the same lines, do you think disentanglement representations are a tool strictly for like a machine learning engineer, or might they propagate all the way to the user?
I think that's a very good question. If you manage to learn disentangled representation in a way that the components that you learn, the factors of variation that you learn within the representation of specific users, if you can connect those back to some attributes of the different items in your catalog, then you can theoretically allow users to control those specific parts, those specific factors of variation within the learned representation. So going back to the example of t-shirt, if you want to change only the color of the t-shirt, you should be able to see only red t-shirts in your recommendation. So a platform could use those disentangled representation as a way to give more control to the user, and in a way they can control how they want to shape the different recommendations that they are getting.
So in your work, you found a correlation then, and correct me if I'm wrong, but there is a link in some sense between disentanglement and interpretability, not so much so between effectiveness and disentanglement. With those results in mind, what do you think the future of the idea of disentanglement should be in recommendation systems research?
I think we should focus more on, of course, try to have as much as possible reproducible results in future work. But then again, also try to provide a quantitative evaluation of learned disentanglement, because that is very crucial. I think the study of disentanglement representation is very important from the interpretability point of view, because, yeah, we did indeed find this correlation between the two. And I think if we explore even more in that direction, we can provide even ways to improve even the performance of the recommender system if we couple it with other components within. Because from our study, we saw that relying only on the disentanglement component did not provide connection to the performance of the recommender system.
I know this may be out of scope for the particular paper we're discussing, but you, in the introduction, mentioned your work also involves large language models, which are, of course, the topic du jour everyone is getting into now. Could you talk about how they're impacting your work?
Yeah, so in the very beginning, I was trying to stay away from the LLM field, but they are everywhere right now. So I sort of shifted a bit from representation learning in recommender systems to large language models. We recently had a paper accepted on trying to denoise user profiles with the use of large language models. So what happens in a normal recommender system is that you make use of implicit data instead of explicit data. So implicit data is just some actions that you usually do when you interact with the recommender system, like some specific clicks or watching a movie up to a certain minute. And because these kind of data are much more abundant, industry ends up using this data to train the models. The problem is that this data by design is noisy. So you might watch a specific movie, but in the end, you end up giving a dislike, or you purchase something on Amazon, and then in the end, you leave a negative review. So when you build a recommender system using this noisy data, then of course it might affect the overall performance of the model. In this latest work, we tried to use LLMs to try to denoise, find items in the previous interactions of the users, find items in the previous history of interactions of the users that are noisy. And if we were to train the model without those specific items, that would bring better performance to the recommendation model.
That's an interesting idea. Do you have any thoughts on how we identify which ones are outliers in that fashion?
Despite the hype, LLMs still act a bit like black box. So yes, in this work, we try to use LLMs and ask it basically to pick which items to remove from the history of the user. But again, we do not know why it shows specifically those items. Yeah.
And we touched on this a little bit already, but you'd mentioned some of the challenges in reproducing results during your literature search. I'm sure there are many academics listening now, getting ready to publish their paper and their work in recommender systems. Could you give any advice for how they could better prepare their publication and whatever else they release to make it more reproducible?
Yeah, I think there are some steps that they can take to achieve a more reproducible work with their paper. One thing which I believe is quite important is to make it as much as possible to release their code, and very importantly also give specifically the hyperparameters of their best results. Usually what happens is that we include a range of hyperparameters when we do the hyperparameter tuning part when training the models. But it's very important to also have specifically which hyperparameters produce the results that end up being reported in the paper. Another component is also releasing the data, and specifically the data splits that were used. So yeah, overall, this allow other researchers to replicate the results.
Good advice for sure. What's next for you in your career?
Right. So right now I'm doing an internship with Amazon where I'm working. I switched from recommended systems for this internship, and I'm focusing mainly on large language models, specifically in model merging.
And is there anywhere listeners can follow you online?
Sure. They can reach out to me on Twitter or LinkedIn.
Very cool. We'll have links in the show notes for listeners who want to follow up. Ervin, thank you so much for taking the time to come on and share your work.
Thank you very much for having me.